Welcome to the Explainer. Today, we are going to tackle something that can look, well, pretty impossible at first glance, those messy, mixed-up resistor circuits. But don't worry, we're going to untangle this puzzle, and I'll show you a super straightforward way to solve them every single time. So here's the game plan. We'll kick things off with a gnarly-looking circuit, do a quick refresher on the basics, then I'll show you the simplify and redraw method. We'll walk through two examples, one simple and one a bit tougher. The goal? To get you from confused to totally confident.
Visit youtube.com/avidsystem and don't forget to subscribe.
All right, let's get right into it with our first challenge. You're about to see how we can take something that looks super complicated and just break it down into easy, bite-sized pieces. Okay, so how on earth do you solve this? I mean, look at it. You've got resistors going every which way. Some look like they're in series, some in parallel. It's a bit of a mess, right? The big question is, what's the total resistance of this whole thing? It looks like a tangled web, I get it, but I promise you there is a super simple, logical way to get to the answer. Okay, before we try to solve that puzzle, we got to make sure our tools are sharp, right? So let's do a super quick refresh on the two golden rules of resistor circuits. You probably already know these by heart, but it never hurts to double check. And really, that's it. It's just these two things. For series circuits, the key is that the current is the same through all of them, and you just add up the resistances. Easy. For parallel circuits, the voltage is the same across all the branches, and you use that reciprocal formula. Seriously, these two basic ideas are the only tools you're going to need. That's the secret. Okay, now for the master technique. I call it the simplify and redraw method, and it is an absolute game changer. This is the strategy that lets you take a big, hairy problem and just chop it up into a bunch of simple little ones. It's all about making the circuit easier to see with every single step. And this quote right here, it hits the nail on the head. You see, the trick isn't just doing the math. You could try to do it all in your head, but that's where things get messy. The real key, the thing that makes this all click into place, is to redraw the circuit after every single change. It's a visual aid for your brain, and trust me, it makes all the difference. So it all comes down to this simple three-step loop. Think of it like a mantra. Identify, calculate, redraw. First, you look at that messy circuit and identify one simple part, a couple of resistors in series or in parallel. Next, you calculate their combined resistance. And then, and this is the most important part, you redraw the whole circuit, replacing that pair with their new single equivalent resistor. That's it. You just do that over and over until you're left with just one resistor. All right, enough theory. Let's get our hands dirty. Let's take that method and apply it to that first puzzle we looked at. We are going to watch that confusing diagram shrink down into one single simple number. Okay, first step, identify. We're hunting for the low-hanging fruit here, the easiest part to deal with. And if you look at the diagram, R2 and R3 are just sitting there, one after the other. That's a textbook series pair. That's where we start. Step 2. Calculate. Since they're in series, this is super easy. We just add them up. 8 ohms plus 4 ohms gives us 12 ohms. Let's call this new temporary resistor RA. And now for step 3, redraw. Imagine you literally take an eraser to R2 and R3, and in their place, you draw one single 12 ohm resistor. See? The circuit's already looking a whole lot cleaner. Okay, back to the top of our loop. Step 1, identify. Now take a look at our new, simpler drawing. Our brand new resistor, RA, is sitting right next to R4, and it's pretty clear they're connected in parallel, right? So that's our next target. Step 2, calculate. For two resistors in parallel, you can use that handy product over sum formula. So 12 times 12 divided by 12 plus 12, that gives us 6 ohms. And you know what comes next, right? Step 3, redraw. We wipe out that whole parallel section and replace it with a single, neat 6 ohm resistor. And would you look at that? After all that identifying and redrawing, our big tangled mess has been reduced to this, just two resistors in series. We've got the original R1 and our new combined resistor. We're in the home stretch now. So one last time through the loop. They're in series, so we calculate by adding them up. 6 ohms plus 6 ohms, and that gives us our final answer. That is the total equivalent resistance for that whole crazy circuit we started with. And there you have it, 12 ohms. So what does that mean? It means that whole complicated network we started with its 4 different resistors, well, electrically, it behaves exactly the same as one single, simple 12 ohm resistor. And we figured it out just by taking it one tiny, simple step at a time. Okay, that was a great warm-up. You ready to level up? Let's put our method to the test with a bigger challenge. This is a resistor ladder. And yeah, I know, at first glance, this thing looks way more intimidating.
Now, this might look a lot more complex, but here's the cool part. We are going to use the exact same strategy. The only trick to know for these ladder-type circuits is where to start. You always want to start at the end, the side that's furthest away from the voltage source, and then you just work your way back towards the beginning.
So we're just going to put our identify, calculate, redraw loop on repeat. We start way over on the far right. First, you'd combine R8, R9, and R10. Calculate their value, and then redraw. Now that new resistor is in series with R7, so you combine those. Redraw again. Now that new chunk is in parallel with R6. See the pattern? You just keep doing this, collapsing the circuit one step at a time, like you're squeezing an accordion, working your way from right to left. And after you go through all those steps, all that identifying, calculating, and redrawing, that entire 10-resistor beast of a ladder network shrinks all the way down to a single equivalent resistance of just 10 ohms. It just goes to show you, the method works no matter how scary the circuit looks at first. Okay, so we've broken down two pretty different circuits. What's the big takeaway here? What have we really learned? Well, the most important thing to remember is this. You can solve almost any complex resistive circuit if you just stop trying to solve it all at once. The secret is to break it down. Find the small, simple pieces, solve them one by one, and just systematically chip away at the complexity until the final answer is staring you right in the face. And you might wonder, why does this even work? Well, it's because deep down, that's what these circuits are doing. A series circuit is just a voltage divider. A parallel circuit is a current divider. So every time we combine resistors and redraw, all we're really doing is simplifying one of those little divisions. And we just keep doing it until there's only one single path left. Now, this identify, calculate, redraw method is an incredibly powerful tool. I mean, it'll solve the vast majority of circuits you're ever going to run into. But it's not a silver bullet. You should know there are some tricky circuits out there, things like bridge networks, where you can't just keep simplifying like this. They require a whole other set of tools. So the next time you see a circuit that looks impossible, your first thought should be to try this method. But if it doesn't work, that might be a clue that there's something even more interesting going on under the hood.
Thanks for watching.